Thank you very much for coming to this talk. Been introduced. I'm a research engineer on the EconArc project, which is a NumFOCUS sponsored open source computational macroeconomics toolkit. And I will be talking a bit about what's going on with open source software and economics, especially macroeconomics, and recent advances in using deep learning to help with these kinds of tools, and then briefly talk about where we think things are going in the near future. So the story of computational macroeconomics and open source might start in the mid-90s with a software tool called Dynaire, developed by Mikhail Julliard at the Bank of France in 1994. And this is at a time when in macroeconomics, what's really big are dynamic, stochastic, general equilibrium models, which make a lot of very strong assumptions in order to be tractable at the time. So this involves representative agent modeling, which means you take an entire sector of an economy and you collapse it into one agent that's sort of optimizing its problem in that part of the economy. And then you make assumptions about complete markets, things are clearing in certain ways. And these assumptions make the models tractable, and it really becomes the mainstay of macroeconomics during this period. And Dynaire provides, it's still ongoing as a project, like a domain-specific language for defining these kinds of models. So you could very easily spin up a real business cycle analysis model. And it was originally written in C, and they rewrote the preprocessor in C++, and they made these models that were preprocessed portable to MATLAB and Scilab and GNU Octave, and very recently they're now porting this to Julia. And this kind of proves that some kind of computational macroeconomics is useful to the world. But the great financial crisis of 2008 really threw a lot of these methods into doubt. Right? This dynamic stochastic general equilibrium representative agent paradigm could not predict, understand why there was a great financial crisis. Because to explain that crisis, you need to be able to have speculative asset bubbles, heterogeneity in agents, so some people get affected by the crisis more than others. You need incomplete markets. And so there became a lot of pressure on the economics community to really take seriously different kinds of more complex models. And around the same time, there's a lot of new software paradigms, which I expect this audience is amply familiar with. So faster versions of Python that mean you don't have to code things directly into C++, Julia, GPU programming, new open source development workflows, new computational science presentation tools, and into that environment, a new wave of open source tooling has emerged. One of the notable projects is QuantEcon, which is another NumFOCUS fiscally sponsored project, and it really made waves within economics because Thomas Sargent, who's a Nobel Prize winner, is one of the kind of leads on it. So it's very difficult. Economics is a very slow-moving field. It's hard to build legitimacy with it, but when a Nobel Prize winner puts their stamp on it, it's good to go, right? So so Thomas Sargent and John Stachurski and others have started looking at QuantEcon. I think it's several years old now, but really it's lecture notes in computational notebooks, and then like a lightweight library of building blocks that are used in the curricula that sort of perform sort of utility functions. And you can go explore it. It's sort of the basic building blocks for economics teaching. They have it in both Python and Julia. But this has gotten like a lot of people excited within economics of using open source tools. But in terms of like actual modeling, building more complex models, the trend now is towards heterogeneous agent modeling. So rather than collapsing that entire sector into one agent, you start to say, well, actually, the economy realistically has a wide, range of different kinds of, for example, consumer households, and they may be affected by unemployment differently. They have a distribution of wealth rather than a single concentration of wealth. So this Purcell-Smith model is one of the earliest heterogeneous agent macroeconomic models to really take off, and it's used as sort of like a test case for a lot of these new methods. But the problem is that the more complex the models are, the harder it is to solve, right? You get computational complexity with these higher dimensional models, and heterogeneous agents imply that you have agents that have to anticipate many other agents working in the economy. So they're high dimensional almost by definition, unless you do a lot of tricks to make them more tractable. So just to make this a little bit more concrete in terms of sort of notation, I'm taking this notation from this recent Miller paper. So we've got an optimization problem, an intertemporal choice optimization problem. There's an exogenous state process. It's a Markov process driven by this epsilon noise that comes in at every period. And there's an endogenous state process, S, that's being driven by both the exogenous process and a choice, X, which is, it has to satisfy some sort of constraint. So like capital X is like constraints given the current state of my choice. So for example, the exogenous process might be, in many models, my labor income, my endogenous state is my bank balance, and my choice is how much to consume today. Right? And the problem is to maximize expected discounted reward, where the expectation is over all future shocks and given some current starting place. And the solution to this problem is a decision rule that when I see that I'm in a particular state, that includes the exogenous and endogenous state, if I make this decision, I'm going to maximize that discounted future lifetime reward. And some other notation just here. If you have a parameterized decision rule, parametric decision rule, that's where you've got some bunch of parameters, theta, and you want to choose those parameters theta so that your decision rule best approximates the true optimal decision. So that's the notation in general, and the way people have been doing things, I want to say, past 20 years, this is, well, at least, I mean, dynamic programming solutions also are using this dynamic stochastic general equilibrium framework. So they've been adapted to these heterogeneous agent solutions as well. So this is a Bellman equation. It turns that lifetime reward problem into this recursively defined function, and it can be solved using dynamic programming. So you're searching over a grid of state spaces very systematically. Reinforcement learning techniques use the same kind of setup framing. For some reason, they aren't used very much in economics per se, because the economists love exact results. But you could use that, and then if it's a finite horizon problem, you could use backwards induction, which is essentially dynamic programming, only you have a finite end state, so you just iterate backwards. So, and then this is one of the many dynamic programming algorithms, the simplest, maybe the worst, but also the easiest to present. And essentially, for each state in the state space, you update your value function each step in the loop with the currently observed reward and discounted expected future utility based on the current state of the value function. You keep iterating that until it converges, and you get to, provably under a number of conditions that I won't elaborate on, you get to the true value function from which you can get the policy function to read it off. And there's, yeah, sure, question?
Sorry. So in each step, you're just trying to maximize your decision, figure consumption decision.
Okay, so this is yeah, I can explain that. So this is to try to converge on the value function, and on each step, you update the value function for each state. So you look at every state, and here we're assuming a finite number of states. And then for that state, you say, I'm gonna take my
earlier value function and plug it in here. And then I do need to optimize this value for all available choices given that state, right? And then you take that value and use that to update your value function for that state, and then you continue. A problem with this, so there's a couple expensive parts of this. That optimization step can be expensive. There are tricks to make it less expensive. But the thing that actually winds up killing this method is that in most economic problems, you're dealing with a continuous state space. You know, like money is real value, right? So you have to discretize those continuous spaces to use this method, because you need to iterate over a finite number of things. And then you have to do interpolation over the values that you found on those grid points, and that interpolation step winds up being quite costly. But also, if you have a high dimensional space and you're discretizing every dimension, you wind up with an exponentially large problem. And so this is one of the ways the Pearson dimensionality shows up in the sort of Bellman equation-based problem. Okay, but nevertheless, these methods are have been until recently kind of the best thing available, and there's been a number of software tools that use those and try to make modeling this way easier. One of the nicest is Dolo, and Dolo provides in a rather interesting way that's reminiscent of Dynair, a kind of YAML-based configuration file for describing models, which then gets parsed and it can compile into, there's a Python and Julia compiler for these. The Python compiler is very highly optimized for GPU and Numba and a bunch of other things. And it's there's a lot going for it. You can express a wide range of models. There's many solution algorithms implemented, including the dynamic programming solutions that I talked about before, also projection methods that I won't explain because I don't understand them. And then given a solution that can simulate forward the Markov chain that the model implies using a transition matrix method. And it's a very impressive piece of work. It does have some limitations. It doesn't do time varying problems. So if you limit things to a time invariant infinite horizon problem, then you wind up with essentially like an ergodic solution to the problem that's a Markov chain, and that's easy to analyze. But if you want to have more complex things like a life cycle problem where people at different ages have, say, different income streams and different probabilities of death, and then you want to have overlapping generations, so you could see the equilibrium under those conditions, Dolo won't do that. Dolo also doesn't have things which help you do market aggregation. So if you have agents sort of consuming and laboring over time, but they want to pool their capital into a resource that then generates productivity in the economy, and that economy then distributes the wages out to the agents, which is what happens in one of these typical models. There's no support for that in Dolo at the moment. There's some experimental options, but they haven't been integrated. HARC, which full disclosure I work on, has some similar scope. It's Python only. A lot of it is about supporting this endogenous grid points method, which is a trick to basically make that optimization step in the dynamic programming algorithm constant time. And it has a somewhat wider range of models, including those life cycle problems that I was talking about. It uses Monte Carlo simulation for producing the results of a model, and it does have this sort of population dynamics. You could have agents that die and then get reborn and possibly pass on wealth to other generations or spread it around, which is something you would want to model if you're trying to model a macroeconomy. And it does do some of this market aggregation, for example, is used in the Purcell-Smith model. So there are some downsides to HARC, which is that it relies a lot on the hard coding of certain model features, and we're working on refactoring some of the things that could be more modular. There's a lot of work going on in hardhat at the moment, but it's another one of the tools in this space. But what's really shaking things up in this field now are deep learning methods as applied to macroeconomics. And so most of the rest of this talk is going to be about rather recent work describing how to leverage deep learning to basically defeat some of this curse of dimensionality that we're talking about. And there's this Mailer not paper, which I'll be drawing on a lot. There's another similar paper by Zinovich, Gagov, and Scheidegger. There's a Chen, Bishop, Scheidegger, and Chasson Creel paper that are about estimation that I'll also touch on. So for deep learning for heterogeneous agent macro, this is the Mailer-Vermont technique. The overall strategy is basically to use the objective function of the neural network that you're training to encode all the model equations that are important. So unlike in a kind of deep learning classification task where you're looking at, say, mean squared error between something you're trying to predict and the results of the model based on some training data set, here what you're doing is you're defining the optimization problem, and you're just using the neural network as a generic sort of function finder, and it's finding the function that optimizes that equation. Right? So the question is, how do you turn all the relevant model equations into a function such that minimizing it solves for everything, including the optimal policy of the agents? And the trick that Mailer will not use is they have to combine all the model equations into one operator that includes not just all future shocks, but the randomized initial state. And this is, again, this is in a time invariant setting. So there's just a probability distribution of where you start, and then there's a probability distribution of where you go. And while it's iterating over time, there's an ergodic distribution that's stable. So they've got a whole, I'm going to skip ahead to the example just to make it a little bit clearer. Right, so one of the sort of simplest ways to do this is you say, like, this is a problem, this is a consumption saving problem. Somebody, this is a person, they have wealth and they consume out of that wealth. Anything they have left over after they consume, it gets affected by an interest rate. They earn income every period. Their income is a random number that's a log normal distribution, right? And one way you could do this is you could just encode that lifetime reward function directly into the optimization function of the neural network. And it turns out that works okay. There's cleverer ways to do it where you use the Bellman equation or you use the first order condition of the optimization problem, and you can compare those results and compare different neural network architectures. But this one works fine for presentation and works surprisingly well if you use their algorithm. And so this is the algorithm they use. And it's quite interesting. So remember that when I was talking about dynamic programming, we're saying that that relied on a grid over all the states, right? And that led to this curse of dimensionality because the grid is, exponential of the number of dimensions, right? But instead of using a grid here, what they're doing is they sample from the model. Like at each step of the algorithm, they have a model, and you can sample from the model using Monte Carlo sampling. And then when they compute the empirical loss to retrain the neural network, rather than training on an entire grid, they just train it on top of that sample. And that sample can be any size, but it is probabilistically reflecting over time. It converges on this ergodic distribution of the simulation, which is much more compact than the entire grid space. Just to do an intuition, so if I've got like a 1D, so I want to compare like a unit cube and a unit sphere, right? and I've got like a 1D unit cube and 1D unit sphere, they've got the same volume, right? If I've got 2D units, now I've got this square, and I've got this circle, right? And the circle is smaller than the square. 3D, now, I think actually if you look at the comparison of the volume of the sphere and the circle, it actually goes up a little bit, but then it starts dropping down and out. As you get higher and higher dimensions of the sphere, it's a smaller volume relative to the cube, hypercube. So that's. And if we're sampling from a probability distribution, the probability distribution has to have unit mass of 1 total, right? So most of the parameter grid is never going to be reached, especially if there's things in the model that are driving it to convergence. So this makes a lot of things doable that were not doable before. This is the whole algorithm. I think I'll just go through it again, just because why not repeat myself and talk about something complicated. All right, so you have to construct this this risk function, this objective function, and that is basically describing an optimization problem and its constraints. You have some sort of sample, you have a starting sample from the model, and you define the empirical risk on that sample. You have some neural network, which is this parameterized decision rule, right? And then you fix the initial vector coefficients, so you initialize the neural network, and you start training the machine, and you start finding this theta that optimizes, or so that minimizes empirical risk by simulating a lot of data, and then you get the gradient of the cost of running the model on that data, and then you update those coefficients, and that's just back prop on a neural network, right? And then if you converged, you stop, right? And then you look at whether it's good enough. And if it's not good enough, then maybe you have to change your architecture. Maybe your activation functions are not the right properly set. And that's kind of where the field is a bit sort of moving. So we already talked about that problem. Okay, how am I for time?
10 minutes.
10 minutes. I'm just going to keep going and do questions at the end. Maybe you don't mind. Okay. So estimation is like a different sort of problem entirely. So so say you have a model, you've got these equations, you've set up what the agents are supposed to be doing, what their incentives are, right? And then you can solve the model and you get the optimal decision rule. But maybe, this happens a lot, there's a bunch of free parameters in the model that stand for things that are empirical, right? You might have mortality rates be a parameter of the model. You might have income streams be a parameter of the model you could get from, say, the IRS, right? Sort of general income streams. You could have all sorts of things that you would actually want to track and use data to calibrate are going to be these parameters. Right? And one question you might have is, assuming this model, but not assuming the parameters of the model, and knowing that there's certain things that I want to target with the model, like interest rates, right? What parameters do I need to make the model predict those interest rates? Okay. So this is kind of a structural estimation, sort of abductive inference kind of task. And assuming, let's see, where was I? Okay, so you have the model, you're able to solve it, but you want to know I'm sorry, this is supposed to be the notation's a little bit warped. point is, if you want to do that optimization, you have to run the model many times, and you might have to solve it many times, and both of those can be expensive. And so what Shindishim and Scheidegger have done in a paper is there's a trick, which is you can do deep surrogate models. So this is also happening in some other fields where you've got really complex agent-based models. Surrogate models are cool. That's when you have a complicated model that's hard to run, and you essentially train a neural network to know the function that the model implies, and then you use that for your analysis. So what you can do is you take your model, and you can and if you're trying to estimate parameters, right? These things that you don't know about your model that you want to somehow fit onto some like empirical results. The trick they use is this pseudo-state trick. So remember, we're talking about having a model, you've got the state space, and then you're saying, well, what's the best thing to do at each state, right? But if you just include the parameterization as a pseudo-state, then you can just start sampling from this now large state space. But whereas before, right, we had this curse of dimensionality, here we've got kind of the opposite sort of economies of scale, right? It's really cheap to sample from this model. You can do it in a really parallel way, and you can get as much data as you want, right? There's no computational complexity to that, right? And then you can basically train a giant neural network to get as close as possible to like something that interpolates all that data. And one of the reasons why this works pretty well is double descent. So double descent is this rather recently discovered property in neural networks where you've got this pattern of, so this is sort of the size of the neural network in terms of number of parameters in each layer. This is the training error, and this is the test error. And when I learned about this stuff, in school, what we were told is there's a bias variance trade-off, right? And if the neural network is too simple, then you try to train that neural network, it's never going to get all the complexity in that data, right? But then if you make the neural network sort of so complicated that it has no error, then it's going to overfit that data, and it's going to be a big problem. So the art of it was finding the sweet spot of the right amount of model complexity that has the right inductive bias with the problem you have, so that you minimize the test error. And then, with all this new GPU stuff, they realized that, well, if you just like blow past this entirely, you wind up getting a double descent, and you start reducing your training error again, and you fully interpolate all the data you had before, and this winds up becoming something like a Gaussian process. I think this is still unknown why this phenomenon happens, but recall that the thing you'd be scared of, right, is if you have noisy data. This is completely capturing, like baking in any noise in that data. But recall that we're just sampling from like a model that we've already made. So the surrogate model doesn't have noise in it, besides the kind of random, like the intrinsic noise of the exogenous stuff that you're sampling. So, so they find this works really well, and then they find that the nice thing about having a deep learned surrogate model is that all the derivatives are just there in the model base. And if you're doing an optimization function, you would probably want to know, say, the derivatives of the outputs with respect to some inputs of interest, such as these parameters, and so it's easier to do the optimization. So this is very encouraging for the field. Oh, one more thing, right? I'm not sure I'm going to explain this properly, but this is hopefully tantalizing. Turns out, if you put the parameters as pseudostates into the model when you solve it, rather than doing, so it used to be that everyone said, well, you have a way of solving the model, and then you have this extra step, which is to estimate the model. And you might have to solve the model, n times as you search the space of parameters that you're trying to estimate. And then some people have said, well, you can just include the parameters in the state space when you solve the model, and then when you solve it, as long as you construct your objective function correctly, you get both the decision rule and the estimation all in one shot. And so this is sort of clobbering a lot of people's ideas of how things are supposed to be done, and it's pretty fun. I suppose the takeaways are that deep learning is making a lot of things that were infeasible more feasible in terms of what you can do in macroeconomic modeling. But where things are at, there's sort of some general libraries for earlier forms of modeling, and then there's ad hoc academic code for new neural network-based methods. And so if I were to predict the near future of where this is going and what the field kind of needs, it's like better standardization around model configurations and APIs, like we've had with Dynair, like with Dolo and Arc, et cetera. But building that out so it's a nice reusable sort of open source set of software tools. And then there's a lot of research needed on how to encode models into neural networks. And I've only just touched on that there, but hopefully you can understand why there's both complexity and potential.